Hello everyone. In this video, we will discuss direct sum of abelian groups. So in this section, we will consider only the groups which are abelian, and we take here G to be the additive abelian group. And in this additive abelian group, we assume that 0 is the identity element and minus x will be the inverse of element x. Now, let us assume that G alpha for any indexing set J, let this be indexed family of subgroups of G. Then we will say that these groups G alpha, they generate G if every element of X, if every element X of G can be written as a finite sum of elements of the group G alpha, groups G alpha. If every X can be written as a finite sum of the groups, finite sum of elements of the groups G alpha. Now because G is abelian group, so we can rearrange always such a sum to group together terms that belong to single G alpha. That means we can always write X in this form, X alpha 1, X alpha 2 up to X alpha n, where all these indices alpha 1, alpha 2, alpha n are distinct indices, because this group is abelian group. So in this case, basically, we assume that X is summation X alpha, where alpha belongs to J, the indexing set. Now it is understood because X is a finite sum, and we are writing here X is summation of X alpha. That means X alpha is 0 except for a finite number of elements in this summation. Now, if the groups G alpha generate G, then we will say that G is a sum of the groups G alpha. And we write like this: G is summation G alpha, where alpha belongs to G. And in addition of this condition, if every element X of G can be written as a sum of the elements of G alpha in only a unique manner, then we will say that this is a direct sum. That means if X is equal to summation X alpha, this expression for X, this is unique. That means for every X, there is only one J tuple X alpha with X alpha is equal to 0 for all but finitely many alphas, such that X can be written as summation of X alpha, then we will say G is a direct sum. And in that case, G will be denoted by this symbol. Summation G alpha, alpha belongs to G. So now we will discuss extension condition for direct sums. And this is a useful characterization of direct sums. So this extension condition is given by this lemma. Now G is a abelian group. G alpha is family of subgroups of G. G alpha, this is a family of subgroups of G. And if G is direct sum of the groups G alpha, then G has this following condition, and the condition is given by this star. Given any abelian group H and any family of homomorphisms say H alphas from G alpha to H, there exists a homomorphism H from G to H such that H restricted to G alpha, this is equal to H alpha for each alpha. So in this condition, we have an abelian group H and we have a family of homomorphisms from G alpha to this abelian group H. Then we want to prove that there exists a homomorphism from the direct sum of these groups G alphas, that is G to H, which is actually H alpha, which is actually equal to the given homomorphism H alpha when we restrict it to the group G alpha. And moreover, this homomorphism H, that is unique. This is our star condition. Moreover, this H is unique. And converse of the theorem, that is also true. And in which sense converse is true? Conversely, if we take G alphas generate G, that means G is basically sum of G alphas. So if G alphas generate G and the extension condition star holds, then G is actually direct sum. So let us prove the lemma. Now firstly we prove the converse. If G is generated by G alphas and the star condition, which is extension property of G, that is true, then G is direct sum. So here we have given with G is sum of G alphas. We have to prove G is direct sum. That means we have to prove only that every element X of G can be written uniquely as a sum of elements of G alpha. So let us take an element X which has two different expressions, say X summation X alpha and summation Y alpha. So we have to prove uniqueness for this X. So we take any particular index beta because summation X alpha is equal to summation Y alpha. So we know X beta is equal to Y beta. And we take our capital H to be the group G beta. And we take H alpha, the mapping from G alpha to H. And the star condition says for any given abelian group H and for any family of homomorphisms H alpha from G alpha to H, there exists a homomorphism. So by this condition, now this H alpha from G alpha to H, this is basically trivial homomorphism. We define this to be trivial homomorphism whenever alpha is not equal to beta. And for alpha is equal to beta, this to be, and if alpha is equal to beta, then this is identity homomorphism for alpha is equal to beta, because we have chosen H to be G beta. So whenever alpha is equal to beta, this is G beta to G beta, and this mapping is H beta. So that will be identity. And for other cases where alpha is not equal to beta, we assume H alpha is a collection of trivial homomorphisms. So by given star condition, there exists a homomorphism H from G to H, which is H alpha when we restrict it to G alpha for all alphas. So it means H of X, this is summation, because it is a homomorphism. So if X is summation X alpha, then H of X is summation of H X alpha, and X alpha is an element of G alpha, and H restricted to G alpha is H alpha. So it is summation H alpha at X alpha. Now we know except for alpha is equal to beta, this H alpha is trivial homomorphism. So H alpha of X alpha, this is just identity element for all alpha not equal to beta. And for alpha is equal to beta, this is identity. So this becomes only X beta. Similarly, Hx can be written as summation h of y alpha, because if we take the expression x is equal to summation y alpha for x, then we get this is h alpha y alpha, and by the same reason it is y beta. So x beta is equal to y beta. Now for the given index beta, we have proved that x beta is equal to y beta. Similarly, we can prove that x alpha is equal to y alpha for each alpha. So the expression for x, that is unique. So it means G is direct sum of the groups G alpha. It completes the proof of the converse part. So now we will prove that if G is direct sum of the groups G alpha, then the extension condition holds. So now we will prove the first part here. Now we have given with homomorphisms H alphas from G alpha to H. We have to prove there is a homomorphism from G to H, which when restricted to G alpha equals H alpha. So we now define H like this. We define H from G to H by, now we know this G is direct sum of G alphas. So whenever X belongs to G, that X is summation X alpha, where this is unique representation of X as a sum of elements of G alpha. Now we define Hx by summation H alpha X alpha. Now since X is equal to summation X alpha, this is actually a finite sum. So this summation X alpha H alpha, that is also a finite sum. So this is basically well-defined mapping. Now we have to prove this is homomorphism. H is a homomorphism, and for that we take two elements X and Y, and let us say their expressions are summation X alpha and summation Y alpha, and both are finite sums. So what is Hx plus Y? That is summation X alpha plus Y alpha at H. So by definition, it is summation H alpha at X alpha plus Y alpha. Now H alphas are given homomorphisms. So it is H alpha at X alpha plus H alpha at Y alpha. So this is summation H alpha X alpha plus summation H alpha Y alpha, and by definition of H, this is just H of X and H of Y. So H is a homomorphism. And by definition, if we take X alpha is an element of G alpha, then this X alpha can be written as 0 plus 0 plus 0 and so on, X alpha plus 0. And this is the unique representation of X alpha as an element of X. So by definition, this Hx alpha, this is just summation of H alpha X alpha, and that is just H alpha X alpha. So we can say H restricted to G alpha, this is just H alpha for each alpha, which proves the extension condition. Now we have a corollary of this lemma. And the corollary says if G is direct sum of G1 and G2, and G1 is further direct sum of the groups H alphas for alpha belongs to J, and G2, this is direct sum of the groups H betas for beta belongs to K, and J and K, they are disjoint sets. Then G is direct sum of H gammas, where gamma belongs to J union K. And this is very obvious, because if we take H alphas to be homomorphisms from capital H alpha to H, and H betas from H beta to H, these two are families of homomorphisms, then by the extension condition, they can be extended to homomorphisms H1 from G1 to H and H2 from G2 to H by that preceding lemma. Then further, G is direct sum of G1 and G2, and these two are homomorphisms, one from G1 to H, another from G2 to H. Then again, by extension condition, this can be extended to homomorphism G2H. This H1 and H2, they can be extended to H. Now this H, because the extension condition holds, so this G is a direct sum by the converse part of the lemma. So from this corollary, we can say that G1 plus G2 plus G3, this is G1 plus G2 plus G3, which is basically direct sum of all these three groups, G1, G2 and G3. Now one more corollary. Now if G is equal to G1 plus G2, the direct sum of G1 and G2, then G upon G2, this is isomorphic to G1. Now here we assume that capital H is G1 and H1 from G1 to H to be identity homomorphism, and H2 from G2 to H to be trivial homomorphism. Then by extension condition, there exists an extension H of both these homomorphisms from G to H. Now this H is a surjective mapping whose kernel is G2. So if we have a surjective map whose kernel is G2, then the domain space over the kernel, that will be isomorphic to the range space, and that is H, and H basically is equal to G1 here. So G upon G2 is isomorphic to H, which means G upon G2 is isomorphic to G1. Now up to this we have done the extension condition for internal direct sum. So now we will do it for external direct sum, but firstly we define what is external direct sum. Now in the previous case we have taken G alphas to be the subgroups of the group G, but here we will take G alphas to be any family of abelian groups. So let G alpha this be any family of abelian groups, and suppose G is any abelian group. Now let I alpha from G alpha to G, this is a family of monomorphisms from the groups G alpha to group G for each alpha, such that G is now direct sum of I alpha G alpha. Then we say G is external direct sums of the group G alpha relative to the monomorphisms I alpha. So in the previous case, G alphas are subgroups of G, and G is generated by the subgroups G alpha. But here G alphas, they are not subgroups of G, but G is any abelian group and G alpha is any family of abelian groups, such that we have group of monomorphisms I alpha from G alpha to G. And now from this monomorphisms, we can say that I alpha of G alpha, they are subgroups of G. And G is generated by these subgroups. In fact, G is direct sum of these subgroups, I alpha, G alphas. Then G will be called external direct sum of the groups G alpha relative to the monomorphisms I alpha. Now this group G is not unique, because when we change the group of monomorphisms, the group G will be changed. So this G will not be unique, but it is unique up to isomorphism. So we have this theorem. If we have a family G alpha of abelian groups, then there exists an abelian group G and a family of monomorphisms I alpha such that G is direct sum of the groups I alpha, G alpha. So for any family G alpha of given abelian groups, we can always find an external direct sum. Uh, and we can always find a family of monomorphisms I alpha from G alpha to G. So to prove this theorem, we take the Cartesian product G alpha from for alpha belongs to J. Now it's a abelian group. If we add, because the family G alpha that is given to be family of abelian groups. So this is a abelian group because if we add two J tuples by adding them coordinate wise, then that will be a group. Now let us take G to be subgroup of this Cartesian product, which consists of only those tuples X alpha such that X alpha is equal to 0 for all but finitely many values of alpha. Now from this product, Cartesian product group, we take only those tuples X alpha for which X alpha is equal to 0 for all but finitely many alphas. Now, given any index beta, we define I beta from G beta to G by letting I beta x to be the tuple that has x as its beta coordinate, and 0 is the alpha coordinate for all x alpha not equal to beta. So I beta of any x in G beta. Now because x belongs to G beta, so this x is basically equal to x beta. So I beta x we define as all the elements 0 except for the beta coordinate is equal to x beta, sorry x, and all other are again 0. Now this is beta coordinate, because we are assuming this x belongs to G beta. So from this definition of I beta, we can immediately prove that I beta is a monomorphism. And every element x of G has only finitely many non-zero coordinates. So x can be written uniquely as a finite sum of elements of the groups I beta, G beta, which means this is a direct sum. This G is a direct sum. This completes the proof of the theorem. Now we prove the extension condition for external direct sums, and the condition is almost same. So let us state this condition. Now here G alpha, this is any family of abelian groups. G is abelian group. And I alpha from G alpha to G, this is group of homomorphisms. And if each I alpha is monomorphism and G is direct sum of the groups I alpha, G alpha, which means G is external direct sum of the G alphas, then G satisfies this extension condition given by star, and that is given any abelian group H and any family of homomorphisms H alpha from G alpha to H, there exists a homomorphism H from G to H such that H circle I alpha, this is H alpha for each alpha. In the previous extension condition, we have proved that H restricted to G alpha. But here we want to prove that H restricted to I alpha, G alpha. So that's why basically we are saying H circle I alpha, that is H alpha. And furthermore, this homomorphism H that will be unique, and converse also true. And converse is true in the sense that if G is generated by the groups I alpha, G alpha, and extension condition holds, then each I alpha, that is a monomorphism, and G will be actually direct sum of I alphas, G alphas. So this lemma is just like the previous lemma, the previous extension condition which is proved for internal direct sum, but the only thing here that we want to prove that each I alpha is a monomorphism. Now given any index beta, we define H is equal to G beta, and we define H alpha to be the identity homomorphism whenever alpha is equal to beta, and this to be the trivial homomorphism when this is not equal to beta. Then by extension condition, there exists a homomorphism H from G to H, which satisfies the extension condition, which means which satisfies this H circle I beta is equal to H beta. And now this I beta, because this is identity homomorphism, H alpha is H beta is identity homomorphism. So right hand side is identity homomorphism. So H circle I beta is basically identity. So it means I beta is injective. So for given index beta, we have proved that I beta is injective homomorphism, which means monomorphism. So similarly, we can prove that every I alpha is monomorphism. So it completes the proof of this result. Now we prove uniqueness of direct sums. Now this theorem says that we have already said that that if we have a family of abelian groups, then the external direct sum group G, that is not unique, but that is unique up to isomorphism, which means if we have two different external direct sums of the given family of abelian groups, then those two groups are actually isomorphic to each other. So in this theorem, we take G alpha to be any family of abelian groups, and let us suppose G and G dash, these are abelian groups, and such that I alpha from G alpha to G and I alpha dash from G alpha dash, sorry, from G alpha to G dash, these are groups of monomorphisms, such that G is a direct sum of the groups I alpha, G alpha, and G dash, this is direct sum of the groups I alpha dash, G alpha. Then we will prove that there exists a unique isomorphism. Then there exists a unique isomorphism phi from G to G dash, such that phi circle I alpha, this is I alpha dash for each alpha. So now here we will apply the previous lemma in which we have proved the external extension condition. We will apply the lemma 4 times here. Firstly, G is direct sum of the groups G alpha, and firstly we take G to be external direct sum of the groups G alpha, that means this, and we take I alpha dash to be the monomorphisms from G alpha to G dash. Then by the extension condition, now this is our group H here. Now given any group H and given any family of homomorphisms H alpha from G alpha to H, there exists a unique homomorphism phi from G to G dash, such that phi circle I alpha is equal to I alpha dash for each alpha. Now secondly, we assume G dash to be the external direct sum of G alphas, and we take I alpha to be group of monomorphism from G alpha to G. Then again by previous lemma, there exists a unique homomorphism, say psi from G dash to G, such that psi circle I alpha dash, this is I alpha for each alpha. So we have applied the lemma twice up to this. Now we define this mapping psi circle phi. The psi circle phi is a mapping from G to G, and this psi mapping has this property: psi circle I alpha dash, psi circle phi circle I alpha. So this is equal to psi circle phi circle I alpha. Now phi circle I alpha, that is I alpha dash, and further this is equal to I alpha. So psi circle phi circle I alpha, this is equal to I alpha for each alpha. And now since the identity map of G has the same property, because if we take identity I mapping IG from G to G, this is identity mapping, then this mapping has also same property IG circle I alpha, that is I alpha for each alpha. And we are saying that this type of mapping that is unique. So by the uniqueness part of the lemma, this phi circle phi, this is actually identity map of G. Similarly, for the other part, phi circle psi, this is identity map of G dash. So now here we have proved that phi and psi are homomorphisms such that their compositions, both the compositions are identity map. That means phi and psi are actually isomorphism. So which completes the proof of this result. So now if we take G to be the external direct sum of the groups G alpha relative to monomorphisms I alpha, then we sometimes write only this type of notation: G is equal to summation G alpha. Because we have proved above in the above theorem that whenever we have two different external direct sums of G alpha, then both are isomorphic to each other. So even though the groups G alpha are not subgroups of G, we will write just this notation: G is equal to direct sum of G alphas, whether it is internal direct sum or external direct sum, because the above theorem proves that internal direct sum and external direct sum both are isomorphic to each other. So it means now we can discuss free abelian groups. So basically these groups G alpha, they can be identified with their image under the mapping I alpha, and G can be considered as ordinary direct sum rather than external direct sum. So now we consider free abelian groups. Now what are free abelian groups? If G is a abelian group, and if we take G alpha to be the subgroups of G, which are basically cyclic groups, infinite cyclic group generated by some element, let us say A alpha of the group G. And then this direct sum of G alphas, that will be called free abelian group, having the elements A alpha as a basis. So we can write here that G is a group, and A alpha, this is indexed family of elements of group G. And if we take G alpha to be the cyclic group, infinite cyclic group generated by A alpha, and G to be the direct sum of groups G alpha, then this group is called free abelian group, having the elements A alphas as a basis. G will be called a free abelian group with this as a basis. Now again we have extension condition for this type of sum, and that is very obvious from the previous extension condition, and let's state that extension condition. Now in this group, in this lemma, G is an abelian group. A alpha is a family of elements of G that generates G alpha, G, And then G will be a free abelian group with basis A alpha if and only if G will be free abelian group with A alpha as a basis if and only if for any, now this is the extension condition, if and only if for any abelian group H and for any family Y alpha of elements of H, there exists a homomorphism from G into H such that H of A alpha that is equal to Y alpha for each alpha, and in this case H will be unique. So in the previous extension condition we have proved that for any abelian group H and for any family of homomorphisms H alpha, we can find a homomorphism H such that H circle I alpha, that is I alpha dash. So here our group G alpha, this is generated by the element A alpha, and this is infinite cyclic group. Now we have previous extension condition holds. Now this extension condition, if it holds, then for any index beta, this A beta, this basically generates a finite cyclic subgroup of G. And if we take H to be the additive integers group Z, then there is no homomorphism H from G to H that maps A alpha to 1. Because if A beta has finite order and 1 does not have finite order, so if we want to show that G is direct sum of the groups G alpha, we have to apply the first lemma. That means this each group G alpha, that is infinite cyclic group. So that will prove that G is free abelian group. Now here basically we are assuming that G alpha is a subgroup of G which is generated by this element A alpha. We have to prove that if G is free abelian group, then this extension condition holds, and if this extension condition holds, then G is a free abelian group. So firstly we assume that this extension condition holds, and we want to prove G is free abelian group. That means we want to prove each G alpha is infinite cyclic group. Now if G alpha is a finite cyclic group, then if we take H is equal to Z and we take a homomorphism from G to H, say this H homomorphism from G to H, then this homomorphism maps element A alpha to number 1, because we are assuming that G beta, this is finite cyclic group, and here A beta has finite order because A beta generates the finite cyclic group, and 1 does not have finite order, so this cannot be a homomorphism. So it means it creates a contradiction. It means G beta, for every beta, that is infinite cyclic group, which means G is free abelian group. Now conversely we assume that G is free abelian group and we want to prove the extension condition. Now G is free abelian group with basis A alpha. Now given the elements Y alpha of the group H, we can define H alpha's homomorphisms from G alpha to H such that H alpha at A alpha is equal to Y alpha. Now this group G alpha is generated by the element A alpha, so we define H alpha from G alpha to H by H alpha at A alpha is equal to Y alpha, and all the other elements of G alpha, they are just powers of A alpha, so they will be defined like this: H alpha of A alpha raised to K, that will be just Y alpha raised to K. So this is the homomorphism defined from G alpha to H. And now we apply the previous extension conditions of the external direct sum. So by that we have a homomorphism, a unique homomorphism G to H, such that this H circle uh, I alpha, that is H alpha for each alpha. So this means H of A alpha, that is equal to Y alpha. Now we apply H circle I alpha at element A alpha. Now I alpha A alpha, that is an element of G alpha, so that will be just A alpha. So H at A alpha, that will be H alpha at A alpha, and H alpha at A alpha is Y alpha. So for every alpha, H of A alpha is Y alpha. It completes the proof of this lemma. Now we have this theorem. If this is a finite, this is a free abelian group with finite bases. Now if G is a free abelian group with finite bases, let us say the basis is given by A1, A2, An, then this n is uniquely determined. Means this n has a fixed value. This is unique, and this is determined by G. Now, if G is free abelian group with bases A1, A2, An, that means G is basically a direct sum of the groups G alphas, where every G alpha, that is infinite cyclic group generated by A alpha. And here this alpha is varying from 1 to n. So this G is basically isomorphic to, now because G alpha is infinite cyclic group generated by element A alpha, so this is isomorphic to Z. So basically this G, this is isomorphic to the group Z cross Z cross Z up to n times. And if we take the subgroup of this G, which is actually 2G, then 2G is corresponding to 2Z cross 2Z cross 2Z again n times. So we can define the quotient group G upon 2G. So this is isomorphic to the group Z upon 2Z cross Z upon 2Z n times, and we know Z upon 2Z that has cardinality equal to 2. So this group basically that has cardinality 2 raised to n. So it means G upon 2G has cardinality 2 raised to n. So whenever G is free abelian group with basis A1, A2, An, then G upon 2G has cardinality 2 raised to n, and 2 raised to n is a constant number. So it means n is uniquely determined by G. And if G is a free abelian group with the finite basis, let us say the basis which contains n elements, then the rank of G is n. Then we say that rank of G is n.